The next speaker is James Derek Fairhead. James was Emeritus Professor at Applied Geophysics at the University of Leeds from 1972 to 2013. And he was the founder and CEO of the GTEC Group from 1976 to 2013. Derek's main scientific research activities has involved evaluating the structure of continental rifting in Africa, with particular emphasis on plate tectonics. With the formation of GTEC in 2005, much research has been focused on improving methods of gravity and magnetic processing and interpretation. And this has included satellite altimeter-derived gravity, microleveling, and the introduction and use of phase to delineate structures at depth via a range of depth interpretation methods. And recently, Derek wrote a book, Advances in Gravity and Magnetic Processing and Interpretation, that was published in 2016 by the EAGE. And I myself bought a copy, and it's an absolute ripper. Today, Derek is going to talk to us about advances in airborne gravity and magnetics. Please welcome Mr. Derek Fairhead.
Okay. Good morning, everybody. I'd like to acknowledge the two co-authors, Gordon Cooper from South Africa and Stefan Sanders, who's probably here and certainly at the conference these days. I'd also like to acknowledge a lot of the manufacturers, contractors who have provided a lot of information so they get their references into this article with the developments that have taken place over the last 10 years. I'd like to concentrate on three main aspects, particularly data acquisition initially, and then look at the local phase and wave number and how these have helped the processing and understanding of the data prior to, say, inversion. And then looking at future developments. In data acquisition, I've subdivided into three areas there. Aeromagnetics, which is a very mature area, and therefore I'm not going to spend too much time on that. Gravity, certainly airborne gravity and airborne gradiometry are very important both to the oil and mineral industries, and there's been lots of super developments over the last 10 years which have really made those instruments instruments of choice when coming to investigate the subsurface. And then in the local phase, local wave numbers, that people have tended to, shall we say, a decade ago, look at the amplitude and the derivatives of the amplitude of gravity and magnetic anomalies. But we now find that if one really looks at the phase of the signal, then you can actually pull out some very interesting information, which is naturally within the other data, the amplitude data, but is obscured because you have the problems of density variations of the subsurface, susceptibility of the subsurface, which through the phase method, you can remove those physical properties and see structure and depth very, very much more clearly than you could with just amplitude data. So let's concentrate first of all on aeromagnetics. This is one of Sanders' aircraft showing whereabouts the various bits of equipment are normally reside. And there's a tendency, I suppose, the instrument of choice is basically the cesium magnetometer, a single sensor magnetometer, which can, which can also be used as a vertical gradiometry in the tail plane. And these instruments are very lightweight, very well developed over the last 10 years. Cesium is probably the instrument of choice, although the potassium system from GEM is got some advantages, and therefore we are likely to see much more use of the potassium system in the future. And of course, we have the aeromagnetic suspended systems away from the helicopter. So this is pretty normal, and you've seen this, these images before. that aeromagnetics is very mature, and with the developments of the instruments over the last 10 years, and also the compensation systems within the aircraft, there's just a continuation of improvement and resolution in the aeromagnetic system. Whereas in gravity acquisition, the three main contenders, you could say, are the TAGS 6, which is on the left-hand side, which is an evolution of the Lacoste-Romberg spring system, through to the Russian development of accelerometer systems marketed by the Canadian microgravity, the center. Of course, you can't see very much of these instruments because they're surrounded by environmental casings and thermal shielding. And also at the far side, on the right-hand side, is the Sander system, the Airgrav system. The important thing about these three systems is that the first two on the left-hand center are commercially available to any contractor to use, whereas the Sander system is proprietary. So that's the difference between these systems. On the left-hand side, we're using the zero-length spring sort of concepts, where the center of the GT2A, which is a further development of the GT1A, and the main development has been able to handle turbulence, and therefore can now do very good drape flying, which the air gravity system has been doing for a considerable time. So there's been a bit of catch-up, as one always has in competition between manufacturers and instruments and providers of data. And the center, the GT2A and the Airgrav, are possibly the systems of choice at this present moment in time. Here is the Russian system, the GT2A, installed in a fixed-wing aircraft and a helicopter. So although they're quite large instruments on gyrostabilized platforms, they just about fit, and therefore can be used in different modes depending on the requirements of the clients. And of course, with the Airgrav system, again, easily installed within a fixed-wing aircraft, in this case a Cessna Grand Caravan, and also in a helicopter system on the right-hand side. The importance of air turbulence and collecting data is expressed in this picture from Sanders, showing that as if one looks at the crossovers or intersection differences between flight lines and the increase in turbulence along the horizontal axis, then one can see that they maintain a very nice, pretty constant effect, that it's not going up and causing huge problems. So we now have a very clear indication that we can do drape flying as well, being close to the ground, and also that the conditions of the air turbulence is not a major factor. Although when the air turbulence gets to such a degree on the right-hand side of the diagram, then there are problems of safety and maintaining the drape and flight path considerations of the survey. And this is showing a drape test survey on the lower diagram, showing the topography and the flight line drape profile, and above that is our 6 repeat lines showing the repeatability of the data, and in this case it's the GT2A. So the main aspect about aeromagnetics over the last decade has been the sensor design has been made more robust, sensitive, and less in weight, and the magnetic compensation system is continuously being improved to remove all the effects of magnetic noise within the aircraft's system. The Airborne gravity acquisition it's been mainly the sensor design and its performance of repeatability and the reduction in the effects of air turbulence, which has caused the major advantage or the development over the last decade in that one can now combine both gravity and aeromagnetic surveys together in a draped configuration so that the cost effects of getting a very accurate gravity and magnetic data are now being solved. Of course, this is probably more important for the oil industry, but certainly very important for regional geological mapping and the implications then for mineral exploration. Gradiometry. This was an added section. I thought everybody was talking about gradiometry at this conference, but I was asked to add a bit on gradiometry. First of all, just the very simple principles that on the left-hand side, the gravity system on a boat, on an aircraft, is basically the gravity response is also a function of the acceleration due to the platform. Whereas if you have two gravity meters, you could say, and you're looking at the difference between the two gravity meters, then the gravity response, or the difference in the gravity response of those 2 meters, is independent of the platform. And this is a major factor that one has to consider. But the problem is that, as one can see with the gravity system, if you've got a point source, then the signal is falling off by 1/r squared. Whereas the gradiometer system is for a point source is falling off by 1/r cubed, which means from the Statoil sort of study that the signal, because it's both falling off with distance, the gradiometer signal, because it's 1/r cubed, is falling off much faster, such that we have a situation where the gradiometer system is very good at seeing shallow responses and is well above the noise level or threshold, whereas gravity can see much better the deeper structures. And of course, the latest developments by Lockheed Martin with Austin Bridgeport with the EFTG is a system which is going to possibly move that black line much further down because of its increased resolution. The 2 systems that are currently in use are the full tensor gradiometry, FTG here. Basically, 3 spinning disks with 4 accelerometers being able to impair so they can measure the difference in gravity on the spinning disks, whereas the airborne gravity gradiometer, the AGG, with the Falcon system, is basically a very much larger disk, about twice as large as the FTG spinning disk, but there's only 1 of these, but there's 8 accelerometers, or 4 pairs of accelerometers. And this is basically spinning in a horizontal or about a vertical axis, so that if one considers very simply, if it was spinning absolutely perfectly horizontally, then one would have this sort of relationship where the 2 accelerations differences in the x and y direction allow you to measure GZZ, the vertical gradient of gravity, very precisely. And of course, because these systems are rather different in their design and performance, there's been a lot of controversy, friendly controversy you could say, about how good one system is relative to the other. I've got a a diagram here showing the average surveyed noise for the AGG system, but for the previous decade, not this current decade, unfortunately. It stops at about 2007. But one can clearly see, in terms of the noise, reducing with time, down to the 2 to 4 Otvos level. Now, if one extrapolates for the next 10 years, then it's down to the 2 or sub-2 Otvos for the AGG. And the FTG, as reported by Geophys, are saying basically they're doing the comparable thing. And one can't help but agree that although there are differences, it's sometimes difficult to compare exactly one system with the other, but the important thing is they're seeing their targets. They're being able to map their targets. They're satisfying their clients in quite a dramatic way. And the competition that they've had between these two systems has really driven the technology, the processing capabilities, such that this noise, which is a very important consideration, has been reduced significantly over the last 10 years. So if one looks at what's been happening over the last 10 years, we've certainly had the use of the 5. Okay, we've got, so you can see this, there's a lot of different sort of subsystems, of which probably the most interesting one is the EFTG, which has just been supplied to Austin Bridgeport. And that is, we're waiting for the results, shall we say, commercial studies to see how well it can do. In fact, they predict it's got 3 times the lower noise level than the existing FTG systems. Advances in airborne gravity have also, in the last 10 years, been in the processing side. And what I'd like to refer to is the tilt angle, the depth estimation, and stable downward continuation. If I don't have time to go all through this, it's in the paper that's been submitted. Basically, the tilt, or the local phase, is this equation here. The local phase is just the ratio of the vertical derivative over the horizontal derivative. The only problem is it's a directional signal, such that it's like a sawtooth signal compared with, shall we say, the analytic signal over a dike. We can actually improve that signal to make it a mappable signal by looking at the vertical derivative over the total horizontal derivative, which is can only be positive, this, although the negative, the vertical derivative will be positive and negative. And to show the advantage of this, this is of an exploration area in Namibia. The yellow is a profile. We're going to go across a lot of features, 1,600 nanoteslas, huge anomalies and very small anomalies. And if you look at the top, those are the conventional profiles, and this is the tilt profile, and you can see that all the small anomalies come out as clear as the very large anomalies, and it's like an AGC effect. The significance here is that the ordinary derivatives are susceptibility or magnetization, a function of magnetization, whereas the tilt derivatives have removed that effect purely because you're dividing one derivative by another derivative, which eliminates the magnetization. The advantage of looking at a derivative, a tilt anomaly, and just picked out one of the, is that the zero crossings tell you where the edges of structures are. The slope of the tilt gives you the depth, and the positive part of the tilt anomaly gives you where the structure is located. So if we go from a conventional RTP map to a tilt map, and then just look at the tilt map with only the positive components, we just removed all the negative anomalies, you can actually start seeing the geological structure. This is a great help to knowing how to interpret that sort of map, which has got such a profusion of information. Here, it's selectively looking at part of that data, and you can start building a structural interpretation. A couple more minutes. Okay, the tilt anomaly allows us to also determine depth, and also the last couple of diagrams is that we can also improve downward continuation. The conventional downward continuation here using Fourier methods can be very, very noisy, whereas if you're using the tilt method, and you look at it in the paper, it's been published by Gordon Cooper, you can get really clean examples of downward continuation without any filtering whatsoever. Into the future, drones, possibly, there's a lot of problems, as we already know, and of course the gradiometer systems of going from this size FTG to the EFTG, which are about twice the size of those disks, and if it's got 3 times the better or lower noise, then this is going to really see information that we've never seen before, and therefore the next decade is going to be very exciting. Although we've seen in aeromagnetics a situation where single sensors have been developed nearly to their maximum, and it's probably the development into the vector type of magnetometer, a three-dimensional vector magnetometer, which might come of age. But here we've got something which is actually in the hands of a contractor, and we're very expectant of what might be happening. Thank you very much.